Now, it may occur to you that the idea of a table and looking up a value in a table is something very common. It's very common, and there are a number of different ways to firstly implement a table, and secondly, to find the function that will do the job that you want. So Haskell contains libraries that have efficient lookup tables. Data.map is the one that comes to mind. That's one efficient way to build and look up things from tables. But it also has some list functions very similar to the one that I just defined. And if we wanted to find those, well, we would of course do so by asking our good friend Hugel. And Hugel would tell us that if we have an element of some key type, and we have a table which looks like a list of key value pairs, and we want to get a value out of that, how might we do that? Well, we actually might be able to give it a bit more information than that, because we can tell Hugel that actually this key type, whatever type that is, has to support equality, because you have to check for equality of the key and the keys in the table in order to do a lookup. So the exact type that we wanted for this function was, if it's an equality type k, then this is the type we want, and we can ask Hugel what it can find for us, and it finds something which is similar but not quite what we were looking for. It finds a function called lookup. So of course the a's and the b's and the k's and the v's, that doesn't make any difference. The difference is over here. It gives a maybe type. Can you all read that? So what's a maybe type? Well, maybe is a built-in, it's not a built-in type, it's a type from the prelude, and it has the following definition. It's a type which is parameterized, a maybe A. What is a maybe A? It's one of two things. You've either got one or you haven't got one. So it's either nothing or it's just an A. So if you give it a type A, maybe A is the type of maybe an A. A maybe int is one of two things. It's either nothing or it's just an int. It's a way of representing in the value a computation which might fail to give you a value. Now you might say that that's a bit strange, but actually it's not that strange. You think about every object in Java. Every object in Java is either an object, really what you wanted, or it's a null. The null doesn't have any of the methods that you would expect it to have. It's just something to represent no object. And so your code all the time has to check, is it the null object? No, okay, then we can, etc., etc. So in a sense, every object in Java is a maybe type. It's maybe an object, but it might also be a null. Now, another reason why things like maybe are very common in Haskell programs is because in the Haskell expressions, there is no sense of control flow. What I mean by that is that there is no obvious order in which computation takes place in a Haskell program. Haskell programs are lazy. So in particular, if I want to build a list from 1 to 10 to the 20, I can do that. And it's a very big list, but if I only want to take 10 elements from that list, it doesn't take me very long to do it. Why is that? Well, because the evaluation order of Haskell is lazy. It doesn't build this whole list and then take 10 elements. It first says, you know, what's the least work I have to do? And then, so the interpreter says, well, give me some result. So take says, well, I can't give you any result unless this list gives me some result. So you build a bit of the list, and then take can give a bit of the result, and then you build a bit more of the list, and take gives a bit more of its result. And so there's no obvious control flow. It's chaos. You do a bit of computation here, you do a bit of computation there. That's the way Haskell computation works. It's great, but it means you can't have a sensible notion of exceptions in a language where there's no sensible control flow, because exceptions are all about control flow. So what you do in a Haskell program is that you represent things like exceptions as values using data types. And maybe it can be thought of as a sort of way of representing a computation which maybe succeeds producing a thing or possibly fails. But it does so without crashing, and it does so without you having to worry about which order computation takes place in. So that's a bit about the philosophy behind this style of programming that is very common in Haskell. So what we could have done here, instead of using the function look, we could have used the function lookup from data.list, and the result of this thing would no longer be an integer, it would be a maybe integer, representing the fact that maybe it will fail. If it fails, it will give the value nothing. So we need a way of turning a maybe something into a something. We would need a way of turning a maybe A into an A. Actually, A is an integer here, but it doesn't really matter. How do we turn a maybe A into an A? Well, there's a function from data.maybe, which converts a maybe A into an A. The main point about this is this will be now the point of failure. This is the function that can fail. So the purpose of the example wasn't really to improve our program, other than to actually show you that there would be a more standard way of doing this by using the from just function. And we import data.maybe from just to make that work. Okay. All right. Before we give some examples of this, I won't bother typing any examples in. So that was before. Let me just make a note that was.